Hi, it's a pleasure to be with you all. I wish, of course, we could have been meeting in Greece. I have this nice scratch-off map behind me, but I think this will have to suffice this year. My name is Pranav Gokhale, and hopefully by the time you're watching this, I'll have just graduated with my PhD from UChicago. This work was done in conjunction with our collaborators at IBM, that's Ali Javadi-Abari and Nate Ernest, as well as from UChicago, Yunong Shi, and my advisor, Professor Fred Chong. Our paper is available right now in arXiv, and of course, it'll also be in the conference proceedings for Micro. And our paper revolves around 4 optimizations for quantum compilation, and all 4 of these optimizations are only visible at the level of pulses. And that means that it's the lowest level of control that we can operate a quantum computer at, as I'll talk about later. In all 4 of these optimizations, we've demonstrated experimentally using IBM's hardware, which now implements the OpenPulse interface. So I'm going to start with describing and talking about the standard compiler stack and software flow for quantum computers. And it starts with a high-level programming language. For example, a lot of people use Python with Qiskit or Google Circ packages equipped in between. And the programming language is really nice to program in, but ultimately to actually run things on a quantum computer, you have to compile it down to an assembly language, such as OpenCasm. And now these assemblies are very nice. They look like hardware description languages, and it gives this illusion that they're really what the hardware is doing natively. And oftentimes computer architects stop here. But the reality is that there's a whole world underlying the assembly. And in particular, the assembly needs to get decomposed or unrolled to a basis gate set, which is like another assembly, but this one is better aligned with what the hardware, the qubits on the hardware can natively do. For example, trapped ion qubits versus superconducting qubits are going to have different basis gate sets. And even this is not the ultimate lowest level of control on a quantum computer. There's no button you could press that'll just execute a C0 gate. Instead, you have to go down to the level of pulses, which are these analog waveforms which are outputted by AWGs, or arbitrary waveform generators. And the AWGs basically produce these pulses that the user can now specify thanks to OpenPulse. So that's the standard flow. And what we introduced in this paper is this approach called augmented basis gates. And this stems from the realization that we'll develop over the 4 forthcoming optimizations that this basis gate set is not actually totally aligned with what hardware natively does. And when we bring basis gates into alignment with the operations that qubits actually natively perform, we end up having a compiler that produces pulse schedules that are far more optimized. They're faster, which is good because qubits have short lifetimes, and they suffer from less miscalibration and error. So I'm going to start by talking about our first optimization, which is called direct single qubit gates. And there's sort of 3 steps in developing this. But first, let me talk about what I mean by indirect single qubit gates. And that's how IBM currently does any single qubit gate, which is, it turns out that any single qubit gate can be described using 3 parameters, a theta, a phi, and a lambda, and then this sequence of Rx and Rz gates, which are rotations along the Bloch sphere. And one important thing to know is that Rz gates can be done virtually, which means that they don't actually take any time or incur any error. They're just done in software. So really, I would think of it as all we have are 2 Rx of 90-degree gates. And that's really nice because from a calibration perspective, it's very easy to calibrate. We just calibrate Rx90, and then along with the free virtual Rz gates, we can now apparently do any single qubit gate. And as an example of this, if we wanted to do this rotation, we do it indirectly, which is first we do an Rz, which in this case is 0. Then we do an Rx of 90 degrees, which takes us down to this point. Then we do an RZ, which takes us across the equator to this point. Then we do an RX, which brings us up here. And then we do a final RZ, which takes us to the target point. And this is what I mean by indirectness. Instead of just going directly here, we went RX, RZ, RX, RZ. And that made sure that our calibration burden was limited. And that's appealing, but one observation is, hey, let's not do RX of 180-degree gates like this, that is flipping from the North Pole to the South Pole. And the reason for that is that it turns out that IBM already calibrates these gates kind of, if you will, by accident, or more so when they're calibrating something else, they're forced to calibrate direct RX 180-degree gates. And it's easiest to see this as pulse schedules. So on the top is the standard indirect way that IBM does RX 180-degree gates, which is that you end up with two pulses that both do 90-degree rotations. And it is true that together they implement 180. But our attitude is, hey, let's just take the single pulse that's a little taller, double as any area under the curve, and it implements 180 degrees in twice as fast. And as we show in our paper, experimentally this works well, and I'll get to that a little later. So the advantage here of doing this is that A, it's faster, and B, it suffers from less miscalibration error. And that's because here, if your 90-degree rotations were actually 89, then you really suffer 2 degrees of loss, whereas here you're only suffering from 1 miscalibration error. So the next sub-optimization here is along the lines of doing Rx of theta, where theta is not just 180 or 90, doing that kind of gate directly. And so if we go back to this motivating picture, we saw that if we want to do this, say, Rx of 60-degree gate, we had to go through all this roundabout indirection. And so one way we could think about doing it, and that's, by the way, represented by this red pulse schedule here, where we have 2 Rx of 90-degree gate humps, but there's a RZ in the middle as well. So one attitude we could take instead is, if we want to just do Rx of 60 degrees, let's just take the Rx of 90-degree pulse and reduce its area under the curve by 2/3. And for some reasons, this is not a totally accurate way to do it. There's these drag errors that come about. But to first order approximation, it's pretty good. And what we did was experimentally test it. So for each of these points from theta equals 0 to theta equals 180, we just took the simple naive approach of scaling down the amplitudes of the Rx of 90-degree pulse or the Rx of 180-degree pulse by the appropriate amount. And we figured out how does it do experimentally by measuring it. And in particular, if I take these experimental results and I project them onto the X plane and the Z plane, we should ideally get this pattern here where it just stays along the prime meridian of the sphere. But we do get some deviation, and that's most likely due to the presence of higher states of the qubit, but that's not really important here. The important thing is that this deviation is actually quite small in the grand scheme of things, and on average, it's better to use it because it's much faster. You only have one of these humps here versus 2 humps. So now that we've developed a way to do Rx of theta, where theta is any angle, not just 90 degrees or 180, we can talk about doing our final optimization in this set, which is doing any single qubit gate directly. And it actually turns out to be pretty easy because there is this ZXZ decomposition, which has now been implemented in Qiskit by Ali, our co-author, based on this work. And all we show is that if we have the ability to do an Rx of theta, then that, along with a sandwich by RZs, which again are virtual, allows us to do any single qubit rotation using just 3 steps. And again, RZs are totally free with 0 duration. So this whole process is only bottlenecked by the Rx of 100, Rx of theta success. So of course, one can wonder how well does this actually do in practice? And so to test that, we did a randomized benchmarking style experiment. And if one is not familiar with randomized benchmarking, basically the way to think about it is that on the y-axis, higher is better. This is the probability of success, basically. And the x-axis is the depth or the runtime of a random quantum circuit that we generate that has single qubit rotations. And so let's only look at the blue and the green lines. So blue represents using our optimized technique, where we do the single qubit gates directly. And green is the standard approach, where all the single qubit gates are done indirectly using that first identity that I showed. And what you see is that the probability of success is significantly higher if we use the optimized technique. You also see that we ran this orange experiment called optimized slow, where we took the optimized approach, which is twice as fast, and we artificially added delays to make it the same duration as the standard approach. And you see that seems to account for a big fraction of the improvement. And that suggests that a lot of the reason that our optimized approach does better is that it's simply faster. It doesn't have two humps, it only has one hump. So now that we've done single qubit gates, let's take a look at two qubit optimizations. And this is called CrossGate pulse cancellation. And the core idea is the following. So as architects and computer scientists, we often envision the gates such as C-naughts or control knots as being just native operations that quantum hardware implements. But the reality is that on an IBM system, if we want to do a C-naught gate, what we really do is this sequence on the right, which involves something called the cross-resonance interaction, which is the fundamental two-qubit interaction that their systems do. And so that's all fine and great. But what if we wanted not just a plain old C-naught, but actually another X gate here and another X gate here? Or if I write it out as actual X's, this. So this, by the way, is called open control C-naught. And if we just pass it to IBM's compiler directly, then this is the pulse schedule that we end up with. And what you notice is that, for example, on the left-hand side, we have two X gates in a row. And that's this double pulse on the left and then the single pulse on the right. And they just cancel out. So it's actually not wise for us to be doing these gates that amount to nothing, but end up just occupying time. And so cross-gate pulse cancellation is just this technique where we realize that we should actually introduce augmented basis gates for the cross-resonance. And that allows these kinds of cancellations to occur quite naturally. And so specifically for that open control knot, whereas this was the original schedule that the standard pulse scheduler produces, we are able to cancel out the X gates and then convert this X gate into a single hump here. And together, this means that our open control knot can be done approximately 25% faster than the standard open control knot. And so that's cross-gate pulse cancellation. So the third optimization pertains to two qubit interactions, and it's actually the one that drives the biggest improvements in our benchmark level results. And the key insight here is that this pattern on the left-hand side is ubiquitous in near-term quantum algorithms like VQE and QA08. And it's called the ZZ interaction. And it looks pretty innocent, but recall that these C-naughts are implemented under the hood using the cross-resonance interaction on IBM systems. And specifically, we need two of them per C-naught. So in total, across the entire left-hand side, we need 4 cross-resonance interactions. Now, it turns out that the entire ZZ interaction as a whole is basically equivalent to just a single cross-resonance interaction, which is really something called a ZX interaction. And the Hadamard gates on the bottom convert the X into a Z. But the point is that if you look at the circuit identity, you see that the left-hand side doesn't really make much sense because we're using 4 cross-resonance interactions to do what the hardware was already natively doing, just to do one of these CNOTs. And so our approach here is just to peel out with pulse level control and an augmented basis gate to isolate that cross resonance and make it a function of a user definable theta. And so we tested this by basically doing the simplest possible way to take a cross resonance and make it variable with our theta on the x-axis. And in short, these results are basically showing that the dashed lines, which are the theory, agree with the experiment, which is the colored lines. And maybe more importantly, if we look at the experimental results for performing this ZZ interaction, on the y-axis here, it's fidelity, so higher is better. We see that on average, our optimization, which is the left-hand side here, does much better than the red, which is the standard way of doing it, which again takes twice as long. So the final optimization that we show in this paper is maybe not so much an optimization as a proof of concept, but it's the observation that we can actually access QDIT or higher level states using pulse level control. And so the background here is that everyone always talks about qubits, which are the 0 and 1 level, but really quantum hardware has natural access to any number of higher states. And usually we don't go there because it requires experimental control. But of course, the beauty of OpenPulse is that we can introduce augmented basis gates that address the transitions not only at the frequency of the 0-1 gap, which is the 0-1 qubit frequency, but also at the 1-2 frequency, which is for the qubit state, and also the 0-2 frequency, which is the other transition in a qubit. And so we performed spectroscopy to exactly find what are the frequencies of these three gaps. And using something called sideband modulation, what we're able to do is basically apply a user level drive that basically takes the qubit frequency, which is this omega 0-1, or in this case, omega D1, and effectively transform it into omega 1-2 or into omega 0-2 by using something called a sideband modulation. And the details are in your paper, but the nice picture is that what we can do is on this plot called an IQ plot, which shows all the outcomes of our measurements, we're able to drive cycles where we go from 0 to 1 in an ordinary X gate, but then we apply our augmented basis gate for the 1 to 2 transition, and then another augmented basis gate for the 2 to 0 transition. And we run that cycle over and over and over. And you can see that we can run about 30 cycles while staying above 70% probability of success, which was a pretty cool result. So since I'm running out of time, just to put this all together, this is applying all of our optimizations, in particular optimizations 1, 2, and 3, to entire benchmarks for variational quantum eigensolver, QAOA, Hamiltonian dynamics, and these are all considered near-term applicable quantum benchmarks. And the y-axis is the reduction in the amount of error, so higher is better. And what you see is that we can do as well as 2x, 2.3x, and on average about 1.4x better using our optimizations. So we think this is an important step towards making quantum algorithms better tailored for execution on the underlying quantum hardware. And hopefully during the live session, I'll be able to take questions and engage in discussion with the audience. Thank you.